Good morning, everyone, or good afternoon. Thank you to the sixth hydrogen session put on by the Hydrogen Energy Center and Valerity. We have been pleased with the participation in these sessions, and the industry is moving so quickly. It's really a phenomenal cavalcade of data information about partnerships, commitments, investments globally. And so we're pleased to make an effort to share some of these developments with you. Today we'll again use the chat function for question and answer, so please populate the chat box as we go. And we'll do our best to address any questions you might have at the end of the session. We also will publish the presentation and the video of the presentation sometime after the session has concluded. I am joined, as always, by the senior board members of the Hydrogen Energy Center who have been diligent in their support of this series of sessions. Rick Smith has certainly been very helpful as the original founder of the Hydrogen Energy Center. And we're happy to see the industry catch up with us, frankly, about the use of hydrogen as an enabling technology for the renewable energy transition that we're going under. Rick, are there any other opening statements today?
I'd just like to mention that we're also planning to post the question and answer session in written form to the extent that we can duplicate it or augment it. Hopefully everyone's questions will get answered. If not live during the webinar, then they'll be able to see answers to their questions later on by going to the HEC website.
Excellent. We also have a hard stop, at least I do, a little bit before 1:00 p.m. So we'll do our best to race the clock to that point. Without further ado, I think we'll get underway. So today, we're talking about a topic called hydrogen hubs. Before we get into that, a little background on HEC and Valerity, and then we'll talk about the market forecast, the global hydrogen market forecast. The enabling technology really are the solar PPAs that have been astounding over the last few months, few years. We'll introduce hydrogen hubs, and it's important to recognize that hydrogen hubs is certainly not an established term. It's defined somewhat loosely. There are hydrogen hubs where hydrogen is going to be stored in depots or used locally. There also are hydrogen hubs where the hydrogen will be put into the export market. And that's really the topic today, is the creation of the global trading market for hydrogen. And hydrogen hubs are enabling centers for that business. And we'll focus mostly on case studies of specific hydrogen hubs and trading relationships, and then talk a little bit about the technology used to store hydrogen for international transport, and then enter into Q&A. We welcome members to the Hydrogen Energy Center. It's a nonprofit professional society. We have engaged in several different activities over the history of the center. One is we certainly participate in expanding knowledge about hydrogen and related technologies in various forums. We also have conducted research for various entities in understanding markets and the opportunities for hydrogen and related technologies. And finally, we've actually engaged in specific projects implementing hydrogen generation, storage, and use in one particular instance that was a solar to hydrogen to electricity project. We welcome any inquiries. We have quite a network of professionals in the industry and a knowledge base. And so we welcome any inquiries you might have to tap into that network. The upcoming hydrogen sessions. Today is Hydrogen Hubs and the Global Hydrogen Trade. Next week, we're looking at sources of hydrogen and focusing on electrolysis. The market for electrolysis is expected to increase between 400 and 800 times in the next 10 to 15 years. I can't imagine being in a business where that kind of increase is even considered. Solar 30 years ago to now would represent an equivalent kind of uptick. So we're in the field of hockey sticks right now with regards to the hydrogen business. The follow-on is hydrogen production with carbon separation. That is a strategy which is undergoing investment around the world. Many companies that have assets invested in petroleum and gas, natural gas, are looking at the marginal cost to decarbonize their systems. And one of the solutions is carbon capture and sequestration. And then June 25th, we're going to be looking at the nexus of wind and hydrogen, which is significant. It's very interesting that the cost to move hydrogen off a turbine in the ocean is less than the cost to move electricity off a turbine in the ocean. But of course, there has to be a market for the hydrogen, and it has to meet the economic criteria for making the project go. Valerity is a consulting company. We're involved in advising energy companies. We've been doing some work recently in the gas industry in terms of decarbonizing strategies and the integration of biomethane, anthropomorphic sources of CO2 and methane, and integrating those sources into the renewable gas supply chain. The clients Valerity has had includes energy companies around the world, both gas and electric, as well as technology companies developing new technologies. I've been involved in the hydrogen industry for 20 years. It began with customers coming to me and inquiring as to the hydrogen market and the opportunities therein. And that has continued right along and really amped up more recently. So what is driving the global trade in hydrogen? Again, it's a geopolitical market. There are places where the energy advantages are strong in terms of resources, and there are places which need energy and are looking for supply chains which can meet those needs in a decarbonized society. And that's really what we're talking about today, which is, where are the markets for hydrogen? How are those markets driving global trade? And what are the solutions that are being developed that make it economic? Just a few years ago, this would seem as a tilting at windmills type strategy, pardon the pun. But again, we're now looking at a market that has a need, and the economics have turned into the favorable box in terms of meeting that market's need. So we see a doubling of global demand for hydrogen by about 2035, 2036. And as we get closer to 2050, we almost see a quadrupling of demand for hydrogen. The base on this chart is the existing demand for hydrogen in industrial markets. That's dominated by petrochemical processes, ammonia production, and methanol production. And those are going to continue, but the industrial will grow as well. with hydrogen seen as a solution for those so-called hard to abate markets, those technologies and applications where it's very difficult to wring the carbon out of the process, either as a chemical feedstock or as a high temperature requirement, hard to electrify. Again, you've seen this chart before if you were on one of our sessions about 4 weeks ago. This is showing Saudi Arabia at the far bottom right, PPA prices, dollars per megawatt hour. We're getting close to 1 cent per kilowatt hour in terms of PPA prices for solar. So you can see in a variety of locations, if it's Saudi Arabia, Australia, even Peru. I mean, these countries have great insulation. Apparently, Saudi Arabia, I think, has 2.5 times the amount of solar irradiation than Germany, for example. So if you're going to locate a solar plant somewhere in the world, those are great locations where the sun is very strong and makes favorable economics. If you reach a price of 2 cents per kilowatt hour for solar, and you can power an electrolyzer, the marginal cost of producing hydrogen results in a dollar per kilogram hydrogen. And that's very competitive. I mean, the cost just for a very large steam methane reformer, the cost of hydrogen out of that reformer in Corpus Christi in Texas, for example, would be somewhere between $1 and $1.50 a kilogram. So solar has become very favorable with the standard gray hydrogen production process. These are a few of the hydrogen hubs that have been announced around the world, representing billions of dollars of investment. We can see that Brazil has come forward with a $5 billion investment. There's a project in the city of Nome, which we'll talk about in Saudi Arabia. Several projects. Australia has really been an early leader in developing the export market for hydrogen. They see the risk of their coal and LNG export market associated with carbon. So they began shifting very early in terms of looking at the potential investment opportunity and return opportunity to keep their resource business going. Australia is a key global supplier of hydrogen and natural gas LNG, and they really want to keep that resource business moving forward in some respect. The Nome project is a $7 billion project overall, and it's important to recognize that there's 2 major pieces to that project. Nome is I think the expectation is to spend something like $500 billion on developing a new sustainable city in northwest Saudi Arabia, and the infrastructure initiative around energy is one part of that project. And we're talking about the ammonia export opportunity that they are developing associated with the Nome project. So the 2 pieces I referred to earlier, one piece is the on the ground Nome facility, which is the left box, and then the other is the global distribution network, which is the box on the right. The Nome project itself is about a $5 billion investment that includes wind and solar, electrolyzers, and then we have nitrogen production in order to produce ammonia. And then ammonia is going to be distributed via ships. And so we see the next phase of this project is the distribution of ammonia around the world to support the truck and bus refueling industry with the ammonia disassociated back to hydrogen at fueling stations around the world. The companies that are involved in this project include Aqua Power, Air Products, and the city of Nome, and they are all 1/3 share partners in the core $5 billion investment project. And then Air Products is handling the $2 billion investment in building out the distribution infrastructure around shipping ammonia around the world and turning that back into hydrogen for refueling. They also have as partners ThyssenKrupp, which is providing electrolyzers, and Alder Topsoe, which is providing the ammonia manufacturing technology. The solar and wind associated with the project is about 4 gigawatts, and they're expecting to produce 650 tons a day of hydrogen, which will then produce 1.2 million tons a year of ammonia. One of the early leaders in developing an understanding about the global market for hydrogen in terms of the technology of actually moving that hydrogen has been Japan, and they've been pursuing a 3-pronged strategy with hydrogen. They are looking to source hydrogen as a major part of their energy strategy in Japan. And they're looking at sourcing that hydrogen both in terms of liquid organic hydrogen carriers, so-called LOHC technology, as well as liquid hydrogen import. And it's likely that they are also going to pursue the ammonia strategy for hydrogen. And what's interesting is, I'll mention now, and we'll touch on it a little later, is that hydrogen converted to ammonia is certainly used in fertilizer manufacturing, and we're seeing initiatives to green up fertilizer manufacturing by greening up ammonia with green hydrogen. But we're also seeing a strategy to consider ammonia for motive power for shipping as a fuel for large ships, and also ammonia being used in turbines for power generation. So we're going to see more about the ammonia strategy in decarbonizing our economy as we go forward. Amazing that Japan wants to procure 300,000 metric tons per year of hydrogen, and they're very aggressively pursuing this. So we'll talk about 2 projects they are pursuing in this regard, and there are more. So the first is this LOHC project, and the LOHC is produced in Brunei. The plant is co-located with an existing LNG facility, which is converting gaseous natural gas to liquid natural gas and exporting that. It appears that what they're doing is using steam methane reformation to produce the hydrogen. There also is a methanol plant next door, so they probably already have an existing hydrogen production facility in Brunei that they're probably just tapping in for that hydrogen. So as such, unless there's some kind of offsets or sequestration, it's not necessarily green hydrogen, but certainly is a test of the technology for bulk transport of hydrogen. And a company called Chiyoda, and I apologize if I'm not pronouncing it correctly, has been working on this technology for storing hydrogen and transporting hydrogen for many years, and have really, their core competence is developing the reformation technology associated with the toluene chain. And we'll talk about that. If I can pronounce this long word, it's a methyl cyclohexane that's then reacted and then turned into toluene, with hydrogen being the taken off, the exit gas. And it's basically hydrogenation and dehydrogenation plants at either end, and it's a cycle that requires the return trip of the underlying chemical constituent. This is a chart that shows the cycle basically, and they've built this facility, and they're actually been transporting MCH, so-called, and transporting back the toluene in this cycle. Certainly, the ship has to be, is being fully commissioned for both sides of the trip. I'm not sure how the economics work on that. Typically, hydrogen in a liquid ship, for example, might consume 10% of the value of the stock in the transport, depending obviously on the distance and so on, and the volume. So it does consume a certain amount of the value in the trip. The hydrogen in this case is being used to power a power plant in Kawasaki, Japan. So this is the hydrogenation plant built and operating in Brunei. This is the tank that is used for the transport, and the photograph does not really tell us how big this tank is. I can tell you it is quite big. I don't have the actual dimension, but I've seen other photographs of it, and it's fairly sizable. So here's a case where a technology has been developed, and Japan is funded the actual use of that technology to investigate its prospects long-term for building a global market in hydrogen trade. And here's the dehydrogenation facility in Kawasaki, Japan. The other project that Japan is pursuing is transporting hydrogen from Australia, the Latrobe Valley, to Kobe, Japan. And again, this is not the cleanest technology per se, but Australia is a bit on their game, because they will be separating the carbon associated with the gasification process here and sequestering it. Fortunately, Australia has spent oil wells that they can use to sequester carbon, and that's the strategy they are pursuing, as I understand it, in this particular case. They will be gasifying brown coal. I think it's sometimes referred to as lignite, and they'll be liquefying that hydrogen after steam methane reformation, and then transporting the liquid hydrogen from Australia to Japan and unloading it in Kobe, Japan. The transportation is they built a ship that holds 1,250 cubic meters of hydrogen in liquid form. This is the ship, again, I apologize for the pronunciation, the Suiso Frontier, 100-meter long tanker, hydrogen tanker, holds 75 tons of hydrogen, and it's fairly impressive, yet again, that Japan is moving forward with this level of investment. Now, what's really fascinating is if you look at the expectation going forward, Kawasaki built this tanker. They have plans to build, if I can see the number, 80 of these tankers going forward. So they expect quite a business to develop in transporting liquid hydrogen around the world. And you can again see this projection of 20 million tons a year by 2050 by Japan for hydrogen imports. So we're going to see quite a growth in this business. Another project announced not too long ago is between RWE in Germany and H2U in Australia. I will note, I don't think it's mentioned here, H2U is developing several projects to produce hydrogen in Australia, and they have an investment by Mitsubishi. So the two projects that we're speaking about, in fact, the one that RWE has an agreement, they're looking to ship 40,000 tons a year of ammonia from Australia to Germany on this first project in the Eyre Peninsula Gateway project. And they're looking at 75 megawatts of electrolyzers to begin and potentially 1.5 gigawatts down the road. I mean, that's a huge jump in capacity. And the ammonia is going to be received at an LNG terminal on the coast of northern Germany. And they seem to have a strategy not entirely clear or crystal clear, but one is to provide ammonia to ships for motive power, and the second is to convert the ammonia to hydrogen and then feed that hydrogen into the regional natural gas system. I will share with you next week an update on the hydrogen plan by Germany. They have, I think, 62 different initiatives around the country. They just announced 2 weeks ago, a fairly significant development. But a network of gas companies is looking to convert a significant number of gas pipelines to pure hydrogen. And so there is a plan underway to see a migration of blending hydrogen into the natural gas system to begin with, and then converting over time in the industrial centers, the development of 100% hydrogen pipelines as they go forward. RWE also is aggressively in the renewable energy business, and they're building one of the largest solar farms in Australia in Limondale. And they see the production of power from solar at about 2 cents per kilowatt hour as being feasible. And again, we can get back to the economics. That implies on a marginal cost basis, $1 per kilogram as being the hydrogen production cost from a beginning perspective. The H2 Hub Gladstone project in Queensland is another hydrogen hub project, and they're looking at 5,000 tons per day of ammonia capacity, ammonia production capacity, up to 3 gigawatts in electrolysis. A very, very large potential project. As you can see, a $1.6 billion facility for the production of green hydrogen and ammonia. So Australia is going all in on the international global market for hydrogen. Now, Brazil has jumped into the mix. The company that is really leading the charge here is called Energix Energy. And the project is called Base One. It's in really the northeastern coast of Brazil. They're looking at a $5.4 billion investment and producing over 600 million kilograms a year of hydrogen. They've already got some form of agreement with a company called Enewind for 3.4 gigawatts of wind and solar, with the potential to scale to 100 gigawatts of renewable energy. And the state of Ceará in Brazil has partnered, and they've identified the Pecém industrial port complex as the loading zone for the product of this project. I'm not clear whether it'll be liquid hydrogen or ammonia at this time. Now, also in the mix is the Port of Rotterdam. Apparently, the Port of Rotterdam now handles about 10% of the energy used in Europe which is really phenomenal. And that means there's a lot of liquid and LNG product that comes into Rotterdam and is distributed into the energy distribution systems in Europe. The Port of Rotterdam has agreements around the world on sourcing hydrogen. They have really put their stake in the ground in terms of being a major port of call for receiving hydrogen and ammonia in whatever form it is as part of the energy transition. So sort of the partnership in thinking with Australia, they see their port running a risk if they don't decarbonize their product set that they're taking in. They have relationships with ports in Saudi Arabia on hydrogen here, and I think there's some others. So they're very aggressively implementing a sourcing strategy around hydrogen around the world. And again, I'm seems to be doing a great job here in managing time or speeding through this presentation, certainly. But this is a chart that shows the different technologies associated with storing hydrogen that can be used. And just to point out, the bottom left, GH2, is gaseous hydrogen. And then far out to the right in the light blue is liquid hydrogen. The bottom is the energy, the content of hydrogen in percentage of weight. The vertical is the energy density in terms of the kilowatt hours per liter. So that's a volumetric consideration. So certainly chemical hydrides, light metal hydrides, they win in energy density and a wide range in terms of content by weight percentage of hydrogen. Liquid hydrogen is a very strong contender. LOHC, MOF, and LH2 are all, equivalent on the energy density. In other words, if you have a ship using all of those technologies, the volume of the ship, the size of the ship will hold about the same amount of energy based on this chart. From a density perspective. Gaseous is just a non-starter, as you can see. Global trade with gaseous hydrogen is just not going to be a happening strategy. And it's really, liquid hydrogen is definitely, a very strong contender. The ships are very expensive. So LOHC is very interesting because the ships, it's just a liquid at ambient temperature, ambient pressure. The ships are no different than ships that are used today. They don't have to be double hulled and kept at whatever the liquid hydrogen temperature is, 283 degrees C below zero. Very, very expensive infrastructure for liquid hydrogen. It works very well. It looks like the transport market is going to a liquid hydrogen distribution scheme. So it might be good on plug and play from that perspective going forward. So with that, I appreciate having the opportunity to present today. Again, I am going to be finishing a little early, but we are open to discussion and dialogue on this fast-moving market in global hydrogen trade.
Brad, this is Rick.
Yep.
I had a question about Saudi Arabia's various initiatives. You mentioned their initiative that would use shipping ammonia as one method. I was under the impression that the Saudis were also actively pursuing a pipeline transportation strategy that would pipe gaseous hydrogen into the European Union. Is that correct, or is that just someone's wish at this point?
Yeah, I haven't seen, Rick, very good question. I have not seen a pipeline strategy for Saudi Arabia. Now, what's interesting is that there is a facility in Portugal, I think, that is looking to ship hydrogen to Port of Rotterdam. But they are also looking at a pipeline to transport hydrogen to go through Spain into France. And pipelines are very obviously costly to build, but they're extremely efficient for transportation. I mean, big ships are the most efficient, but if you can put a pipeline in instead of using a truck or some other means, it's very cost effective. And so they're actually pursuing that. And that's the only indication I've seen of somebody with a source of hydrogen looking to implement a pipeline. Most of these, if you look at the, what would you call it? You bring somebody in and you say, I want to go locate a hydrogen hub. What do I need? Where do I start? Well, you got to start with a desert next to an ocean. That's the criteria. If you want to enter this hydrogen hub business and be competitive on the world stage for hydrogen trading, look for a desert on the ocean, and there you go. So Rick, if you find out any additional information on that, let us know.
Right. I was also under the impression that there might be a pipeline project taking solar hydrogen from places in Northern Africa across to Portugal and Spain, but I need to get some more detail for you on those.
Yes, I think that is a lot more. I think we've seen some, at first they were looking at electric cables, but if you look at the cross either up through Italy or you go up through Spain, the distance that you cover in the Mediterranean is not so great. So that, we might see pipelines. Pipelines for transporting hydrogen are cheaper to build than electric lines. And that's been well established. That's a little bit of why we're looking at wind companies in a few weeks, and they're putting in the offshore wind companies. Some of them are looking at hydrogen, and it's actually cheaper for them to move hydrogen from their offshore wind plants to the onshore demarcation point. But the real question, of course, is what are the conversion losses in producing that hydrogen, and can they cover the gap with the market for gaseous hydrogen once they're on shore? The lower cost of the hydrogen pipeline is not going to make the market, per se, but it's a factor. If you're taking any electricity off a wind plant and converting that to hydrogen onshore, then the math is easier. You could see if you can locate that electrolyzer offshore and save the cost on the electric line, the undersea cable.
So I have a
I
question.
associate Scotland with that. I'm going to encourage people to jump in. We have a slightly smaller group than we've had the past few weeks. So if you have a question or a comment, feel free to unmute yourself and chime in. I see Bob Rosenberg seems to be in that position. Bob?
Yeah, it's a terrific talk and appreciate it. I was just at an energy event yesterday, and the question of the electrolyzers, which I had read about, I had brought up, and what I was told by people who are quite involved in the energy industry, that these are smaller projects which are being put into the US, and that it sounds to me like they're demonstration projects more than anything else. The steam reformation issue comes up as well. And could you give some insights as to how you see the electrolyzers and also the steam reformation approaches?
Sure, Robert, and I appreciate the dialogue, and I'm not entirely clear as to your question is related to markets or technologies, but the European Union has identified putting in place, I think by 2030, 40 gigawatts of electrolyzers. Now, the current market for electrolyzers is maybe 100 megawatts per year. So 40 gigawatts, that's that's a lot larger. That's 400 times larger than the current market. So the reason why they're so aggressive is they're recognizing with high penetration of variable renewable energy, and this is really the key. In fact, I saw an estimate recently. The issue that's being faced is as we move to extraordinary amounts of wind and solar on the grid, we're going to see increasing amounts of power curtailment because the wind and solar is going to be producing power when nobody needs it. And there is no long duration storage available right now. Lithium ion does about 6 to 8 hours right now. And within the next 10 years, lithium ion standard will be, 12 hours to 16 hours, perhaps. But we really need some longer storage, because what's going to happen is this oversupply of electricity. I mean, right now, California curtails enough electricity for about 500,000 homes, full bore. That's a lot. That's several million megawatt hours a year. And that's going to grow. One estimate I saw was that the amount of curtailed power could reach 20% of what we produce every year. And that's just an extraordinary amount of curtailed power. So that curtailed power has got a price point of 0 or even negative because of incentives. And that means you can sop up those stranded electrons with electrolyzers. And there is an issue around the cap cost of electrolyzers and the capacity utilization rate. You can't make money on an electrolyzer if you only use it 20% of the time, but the cap cost is coming down significantly on those systems, which helps in that equation. So we're going to see projects like the project we talked about in Delta, Utah, where electrolyzers will be operating 40% of the time, sopping up cheap electrons in renewable power centers, and then storing those molecules of hydrogen underground in salt caverns for what's called seasonal storage, and really running the arbitrage opportunity between zero cost power and maybe 8 to 10 cent type power on the high end. And that's what we're going to see emerge. It's going to be a very different power system. Is this the kind of thing that you're getting at, Robert?
It is indeed. And that's a significant opportunity, is the way I see it, on the decarbonization issue. So yeah, that was well put together and appreciated. Could you comment on the steam reformation issue? Have you any thoughts on that?
Yeah, what do you mean issue? In terms of carbon or what?
I'm asking a question in the sense that this is an entirely new area for me, this steam reformation.
Oh,
So
Yeah.
that's why I ask.
Yeah, most of the hydrogen produced in the world, that chart I showed of the global hydrogen market, using US tons, that estimate was about 70 million tons a year, if I remember that correctly. Most of that is produced from natural gas, and then a fair amount of it is an off gas. And steam methane reformation is a known process for converting CH4, natural gas into its constituent parts with the water gift shift function. So you're producing CO2, CO, and water, but you're also producing hydrogen. So that's the dominant approach. And there just was an announcement this week about putting a hydrogen hub in North Dakota. And in North Dakota, they have a lignite plant that was developed by the Department of Energy, I think, for $2.4 billion to produce natural gas from lignite. And the plant was purchased in 1989 for $85 million. So the DOE took a big hit on that one. But that plant is now being considered as a hydrogen hub. And what they will do is use steam methane reformation to produce hydrogen from natural gas. It's a very rich natural gas area, North Dakota area, and then sequester the carbon separated in depleted oil wells in that area. And so that's the so-called, there's some people out there which don't, we're trying to get off of using colors, but of hydrogen, but basically blue hydrogen is when you use natural gas, steam methane reformation to produce hydrogen, and then you sequester, you separate and sequester the carbon. So it's a carbon-free approach, but not as clean, certainly, as using renewable energy and electrolyzers. So the decarbonization that's going on around the world, it's not just the new things that are going on, the new hydrogen and so on. There's old hydrogen around, and a lot of it that's used in industrial processes. And we need to decarbonize that hydrogen along with developing new carbon light forms of hydrogen.
Brad, there's a question here.
That's
from
great.
David.
Thank you.
Yep.
There's a question here from David about the Brazil project, pointing out that it looks like it's all private sector. He wants to know if Brazil is given any government support, and also who the end buyer might be in that project.
Right. So it is private. The Brazilian government is supporting, or the state of Sierra, if I can pronounce that correctly or even remember it. I mean, they're doing the port upgrade. So I think they're spending $28 million on that. And that tends, I mean, these are energy plays. And so these companies are going long on these projects. I see another question that asks what LOHC is. It's a liquid organic hydrogen compound, is what LOHC means. I see another question on ASU in the chart with regards to hydrogen. ASU is an air source unit, and it's how you produce nitrogen from the air. And that's going to be a system that's put in place by Air Products technology they know very well. That's how you produce nitrogen.
Kevin, do you want to unmute and maybe ask your question regarding compressed hydrogen versus liquid hydrogen?
Yes, be more than happy to. First of all, thank you very much for putting on this presentation. It's been very educational. So my question is, have you considered or researched into cryocompressed hydrogen, where the density of that cryocompressed hydrogen can be higher than liquid hydrogen? So hydrogen gas at 700 bar and minus 22 or minus 220 degrees Celsius has a density of 90 kilograms per meter cube, whereas liquid hydrogen at minus 250 degrees Celsius has a density of approximately 70 kilograms per meter cube. Just wondering if you looked into that or have any thoughts regarding that.
Yeah, I'm happy to be innocent of many facts of importance around the world. And this clearly is one I am innocent of, Kevin. I've never heard of this. So that might bear looking into. Again, all of these technologies, if you can improve the efficiency of electrolysis, if you can improve the efficiency of the conversion of solar cell electricity production, if you can improve, the density of hydrogen transport, we can begin to see why Japan is pursuing a multi-pronged strategy, because this is what we're seeing in the industry is we can't predict how certain technologies are going to develop. And so, people are definitely looking at riding several horses across the stream, as it were. So how did you hear about this, Kevin?
This has been part of some research from the Department of Energy. So I know some information can be gotten there.
Okay,
All right.
great.
Kevin, do you know whether any of the large companies, Air Products or Linde or any of that industrial gas group, or do any of them make hydrogen available in this form?
I am not aware that they do, no.
Fascinating. Any other thoughts or comments or questions today? I did want to point out there was an announcement last week or recently about a company, I might have mentioned it, called Haldor Topsoe. And they produce the chemicals that are used in materials used in reformation catalysts and amongst other activities. And they've announced a plant in, I think in Europe to produce, I did mention this, 500 megawatts a year of solid oxide electrolyzers. And I think that it's very interesting to see that solid oxide electrolyzers have a higher efficiency of conversion from water to hydrogen. And that is likely going to be a very valuable pathway as we go forward. I mean, those are the kinds of efficiency improvements that we're seeing. We might have a 65% efficient standard electrolyzer, PEM electrolyzer, but claims for solid oxide electrolyzers range from 80 to 90% efficiency, energy in, energy out of hydrogen production. So it's a really big step improvement. Fascinating to see that technology develop. Did someone have some comment?
Bloom has made a similar announcement. Brad, they now make solid oxide fuel cells, of course, but they say they're going to be making solid oxide electrolyzers as soon as 2022, also claiming the increase in efficiency that you just mentioned, but saying that they in particular are aiming at the nuclear plant market, where they think the solid oxide fuel cells are a particularly good fit for one reason or another.
Yeah, you mean they have a funny name for these things. They call them SOEC, which is solid oxide electrolyzer cells. But that's a great point, Rick. Use the thermal energy.
The electrolyzer cells are basically fuel cells functioning in reverse mode. So instead of reacting reagents and generating electricity, they use pump electricity and separate the reagents, and they are critically dependent on catalysts. It's something I did a lot of work on, and you may want to connect with me at a later stage to delve into it, because I patented some ideas that are still to be brought to life. But in essentially replacing the platinum by very, very cheap mixed oxides.
Fascinating, Victor. Thank you for your contribution.
I did a lot of work in this, and it was too early, way too early. But from this idea, I got into making lithium batteries much cheaper, and that still has to fly. It was still early, but now its time has come. But it's a different story.
Yep.
Excellent.
Well, super. I'm getting close to a wrap-up time. I think this has been an informative session. Any final questions or comments, Rick?
No, I think it's a great group, a great discussion as usual. And as I said earlier, we will attempt to put the Q&A from all of the sessions on the HEC website in the fairly near future, so people can take a look at what transpired in the chat, and also it gives us an opportunity to maybe expand a little bit on answering the questions, because we have a little more time to do some research.
Excellent. Well, great. With that, I'd like to extend my thanks, Rick and the HEC team. Thank you very much to the members of the Hydrogen Energy Center. Your ongoing support is important for us to keep these forums going, so that's much appreciated. And all of you on the call today, your active participation is certainly enjoyable. This is how we work. The network is it's a valuable valuable network in this emerging area. So I appreciate that. With that, I think we'll sign off today. Thank you, everyone.
Thanks, Brian.